Hi class, it's Jamie Batts, your instructor for AMP2. We are going to continue with chapter 19, which covers the heart and cardiac function. We're actually getting into the second part of this chapter where we'll be talking about the cardiac cycle and the actual physiology that goes on inside of the heart as it is contracting and beating and pumping blood throughout the body. So this is pretty physiology intense, so I have a couple little demonstrations that I'll do for you and things like that. And we'll start off with the overview of the cardiac cycle. I think I'm going to go to full, oops. I didn't realize it would take me all the way to the beginning of the PowerPoint. So I just think it's better to have it bigger. There we go. So let's talk about the cardiac cycle. So the cardiac cycle is basically the cycle of heartbeats. That's pretty much what it is. So it's the period between the start of one heartbeat and the beginning of the next heartbeat. That's kind of the classical definition. And there's two phases throughout the cardiac cycle. You have the systole phase, which is the contraction or the active phase of the cardiac cycle, and then you have the relaxation or the diastole phase. So the diastole is when the chambers are filling with blood, and then the systole is when they're contracting and squeezing the blood to wherever it needs to go. So the atria will squeeze, they'll go into systole to pump the blood down into the ventricles, and then the ventricles will be relaxed as they're filling, and then they will contract and pump the blood out to their respective circuits. So we'll take a look at how this whole thing works. It's basically a cycle of contraction and relaxation, or systole and diastole. Those are the technical terms. So it is a sequence of these contractions. The ventricles and the atria are contracting throughout this cardiac cycle. The beginning of the cardiac cycle starts with the atria. So the atria contract first. That's atria systole. This is basically pushing and squeezing the blood down into the ventricles. While that's happening, the ventricles are relaxed. So the ventricles are in diastole. So there's an interesting concept, right? The entire heart is not in systole and diastole at the same time, right? It's this series of part of it's contracting, part of it's relaxing, the other part of it's contracting, the other part of it's relaxing. So not just because we're saying systole doesn't mean that the whole heart is contracting. Because think about it for a second. I'm going to try to, I'll go back here. Think about it for a second. So if you have like a heart, right, or a ball or anything that you're trying to squeeze, right? If you're trying to move blood through that structure, if you squeeze the entire thing, everything's just going to squirt out in all directions, right? But if you have this wet sponge, so to speak, and you squeeze the top, where does it go? Down, right? You squeeze the atria, the blood goes into the ventricles. Then the atria relax. Then the ventricles squeeze. And guess what? Those holes, the pulmonary and aortic vessels that are leaving the left and right ventricles, those are going to fill with blood as the ventricles are squeezing. So you have this series of contractions. Atria contract, then ventricles contract. Atria contract, then ventricles contract. If they all contract at the same time, that would be a very messy contraction. You would see that on the EKG. It would be very crazy looking, and the blood pumping would not be efficient. So sorry for that side note there. Let's go back. So the ventricles contract second. That's the ventricular systole. They're pushing the blood into the pulmonary and the systemic circuits. While that's happening, the atria are relaxed. The atria are filling. Because think about it. I keep wanting to go back to me. Sorry. I just think I have a lot of stuff to explain in this one. So as the ventricles are contracting, right, think about what that's doing. That's pushing the blood up and out into the pulmonary systemic circuits. So if you follow those circuits around, what's happening at the end of those circuits? The blood's getting pushed into the atria. So the atria are passively filling at this point. The atria are just getting full with blood as those ventricles contract. Just like as the atria contract, the ventricles are filling with blood. So the opposite chambers are going to be filling while the other is contracting. So while the ventricles are contracting, pushing that blood out into the pulmonary systemic circuits, it's getting pushed through all the capillaries and the veins and eventually ending right back at the atria. Same thing. Atria contract, squeezing down. Those ventricles are filling right below. Sorry, my dog's being crazy. Okay. So there is actually a pacemaker system that is coordinating all of these efforts. So, and that's where we bring in the EKG and that kind of electrical component to the cardiac cycle. The typical cardiac cycle is about 800 milliseconds long. So this diagram here shows it all in action. The heart starts, it's nice and relaxed. Check out what is going on with the valves, right? So you can see your AV valves, your tricuspid and bicuspid valves, and you see your semilunar valves, aortic and pulmonary. They're all closed, right? At this point, the ventricles had just finished contracting. The atria are passively filling from that heartbeat, right? From that squeeze from below. Then the atria contract. When the atria contract, look at the valves. Look at what's open. Our AV valves are open. Our semilunar valves are closed. Our atria contract, and this is that kind of wringing the sponge down into the ventricles. So this is going to fill the ventricles. Once those ventricles are full, they reach this max capacity. There's kind of these little stretch receptors in there sensing how much blood is in there. Our AV valves shut. Notice the tricuspid and bicuspid valves are shut. The pulmonary and aortic semilunar valves open as the ventricles contract. And then after the ventricles contract, we get back to that state of diastole, that state of relaxation. So we have relaxation or diastole, followed by atrial systole and ventricular diastole. Then atrial diastole, ventricular systole, right? Ventricles are contracting, followed by the entire heart relaxing in diastole. So here it is in time, and you can see in this diagram, you can see what's going on at all chambers of the heart. Personally, I like the heart picture better than this, but some people get confused by the different visuals. So this is just another way to look at the same exact thing. So at the very beginning, we have ventricular diastole. They're resting, right? Our atria begin to contract. After our atria contract, our atria are resting, right? This inner green line is atria diastole. Our ventricles are contracting, ventricular systole, right? After the ventricles contract, everything's relaxing, right? Look, atrial diastole, ventricular diastole. For more than half of the cardiac cycle, our heart is just in a state of relaxing. Nothing's pumping. Then the atria contract, and they rest, and then the ventricles contract, and then everything relaxes. And then the atria contract, and while the atria are contracting, the ventricles are relaxing, right? So this whole system, every single heartbeat. Right, that's a lot. You can pause the video here, go back and review this section. I'm going to keep plugging along, and we're going to talk about the different phases of the cardiac cycle. So, as we've said, it begins with all four chambers of the heart nice and relaxed. The ventricles are partially filled with blood because after that contraction happened, after the ventricular systole, not every single ounce of blood that's in the ventricles gets out. There's kind of this reserve that's left at the bottom of the ventricles. So the ventricles are partially full. Then the atria contract with atrial systole. When the atrial systole is going on, that's that wringing of the sponge. Those top chambers are contracting and squeezing that blood down into the ventricles. The AV valves are open. Then the atria relax, atrial systole. This is the beginning. That atrial systole is going to last until they contract again. So it's just going to, the rest of the cardiac cycle, the atria are just kind of sitting there waiting. So they're kind of like the show openers, right? The atria start the show, and then they just kind of wait around until the start of the next show, so to speak. Then you have the ventricular systole. This, the first phase of ventricular systole is actually kind of like an isovolumetric contraction. So here, imagine kind of building up tension and building up pressure. No actual change in volume happens, hence the word isovolumetric, right? But what we have here is this buildup of pressure. All the valves are closed at this point. The AV valves and the semilunar valves are closed. So it's kind of like putting the lid on a boiling pot of water, right? It's boiling, that steam wants to escape, but you put the lid on it, so it's not escaping just yet, right? The ventricles are squeezing and they're squeezing and they're squeezing. They're not getting any smaller yet. They're squeezing. This pressure is building until finally, right, you take the lid off and all that steam erupts out of your pot. It's exactly what happens in the second phase of ventricular systole. This is the ejection phase, ventricular ejection. So that increasing pressure forces those semilunar valves open. The tricuspid and bicuspid valves remain closed, and that blood is going to flow out of the ventricles and into the pulmonary and systemic circuits. So there's two phases to ventricular systole. That isovolumetric contraction, squeezing, lid on a pot of boiling water type of a thing. I like to close my eyes when I talk. I'm weird. And then you take that lid off and you get that ejection phase where the blood erupts out of the heart and goes to where it needs to go. So then the ventricles relax. During early ventricular diastole, they relax, the blood pressure in them drops, and there's some blood that flows back against the semilunar valve. So it's kind of like, imagine a volcano erupting, but not all of that lava making it out of the actual, volcanic hole, the crater, right? Some of it's going to flow back down. It's exactly what happens with the first phase of ventricular diastole. After that eruption, after that ejection, the blood pressure decreases and some of that blood trickles back down the pulmonary and semilunar, or pulmonary and aortic vessels, kind of closing those semilunar valves. Then there's this relaxation that occurs. We're still in, ventricular diastole. All of our valves are closed. There's no change in volume. The blood now, because that heartbeat just happened, that blood is getting passed through the capillaries and the veins, and so our atria are filling at this point. During that ventricular diastole, after that heartbeat, after that ejection, the blood is being pushed through the arteries, capillaries, and veins and ending up back into the atria. So the atria are filling during ventricular diastole. Towards the end of ventricular diastole, our AV valves open, and that blood can just dump right into the ventricles from the atria, and the ventricles are passively filling at this point. And so this period of ventricular diastole lasts more than half of our cardiac cycle, 530 milliseconds. Do you need to know actual seconds? No, you do not. I'm not going to ask you time frame, but in general, you should obviously know what goes on during all of the phases. So there's this whole period of time where the entire heart is relaxed until the next cardiac cycle when the atria contract again. So here it is, all put together in a nice little nutshell. I love this diagram. You're having trouble figuring things out, study this diagram, stare at it, see if you can explain what's going on in each phase. So when our cardiac cycle begins, that's noted by the atria systole. The actual contraction of our atria marks the beginning of our cardiac cycle. They squeeze the remaining blood that's in them down into the ventricles. At that point, the ventricles had already been passively filling from the atria, because remember, our AV valves were open towards the end of the last cardiac cycle. Then our atria relax, our AV valves close, the first phase, that isovolumetric contraction, right, the lid on the pot of boiling water, they're squeezing, the pressure's building, but they're not changing volume yet. They're just building pressure until, right, that ejection phase happens and those semilunar valves are pushed open by that immense amount of pressure inside the ventricles. Blood is pushed through the arteries, capillaries, and veins, and then what that ends up doing is pushing the blood back into the atria. Our ventricles relax, our AV valves and semilunar valves shut, and our atria are being filled from that last heartbeat, from that last contraction or ejection from the ventricles. Towards the end of ventricular diastole, our atria are getting very full at this point, so the AV valves open, our tricuspid, bicuspid valves open, our ventricles passively fill, kind of like just dumping a bucket, right, into the ventricles from the atria. They fill passively. Then the atria contract and the whole thing starts over again. This is the whole thing diagrammed out. Okay, so let's talk about how the pressure changes. This whole cycle is driven by pressure. Actually, any movement in the body, anytime something's moving from one area to another area, it's happening because of pressure. It's happening because of pressure. Our lungs, our digestive system, urinary, it's all pressure. Anytime there's movement in the body, it's because of a pressure gradient or a difference in pressure from one area to another area. So what we have to do to move blood is change the pressure in the areas where we want to move the blood to and from. So if you increase the pressure by opening the aortic valve, that's then going to cause a drop in pressure, right? So increasing the pressure within the aorta by opening that aortic valve, by opening the valve from the left ventricle, right? All that ventricular ejections happening, all that blood is going to rush through that aorta. There's going to be an increase in pressure. Then our aortic valve closes, and there's a drop in pressure because the blood can't pump out of the ventricles anymore. Well, the ventricles are pretty much empty of blood at that time anyways. So there's a short rise in pressure, and we call that the elastic recoil. Our aorta kind of expands just a little bit with every heartbeat, with that kind of explosion, that ejection from the left ventricle, right? That's going to happen every single time. This is going to produce a very small blip, if you will, in our pressure tracing, which we'll look at in a second, and it's called the dicrotic notch. This dicrotic notch is just representing that quick burst of pressure after the ventricular ejection. So here we see this pressure gradient. At the top of the picture, you see the cardiac cycle. Might not look like you're familiar with yet because the drawings aren't there, the actual heart pictures, but the words are there. So you have the whole heart is resting, right? Atrioventricular diastole, then atria contract, right? With atrial systole. Take a look down the chart, and I'm hoping you can see my mouse. I'm not sure if you can. But if you look at the word atriosystole, and then you look down this graph, we're going to see exactly what's happening during atriosystole. So during atriosystole, what's going on in our aorta? This is a pressure graph. The pressure is decreasing in the aorta, right? That kind of makes sense. Our atria are contracting, which means our ventricles are relaxed. So why would there be a whole lot of pressure in our aorta, right? The pressure in the aorta comes from the ventricles, right? So that pressure is declining during atrial contraction. Check what's going on in the left atrium during this contraction. In the left atrium, that's the blue line, we have a rise in pressure. That makes sense because there's squeezing going on. We're moving that blood, we're decreasing the volume and hence increasing the pressure. It's like Boyle's law or something. You do that, and then the blood is going to go down into the ventricles. That's that squeezing that happens. And if we look at our left ventricle, which is the red line, the pressure in there is increasing at the same time. Why? Because we're putting more stuff into it, right? We're dumping the blood into it. So of course, there's going to be a rise in pressure there. Look what happens immediately after those AV valves close. So after that contraction, right, that ringing of the sponge, our AV valve shut. Remember what happens after our AV valve shut. If you can't remember, look up here at the top of the graph. Our atria contract, our AV valve shut, then we go into ventricular systole. Then our ventricles get ready to contract. Remember, the first phase of ventricular contraction is that isovolumetric contraction. That's squeezing, right, the boiling pot of water with the lid on it. That's what's going on right here. And look at the pressure in the left ventricle. This red line goes through the roof, right, until bloop, the aortic valves open. Look at what happens when the aortic valves open. The pressure in the aorta skyrockets. The pressure in the left ventricle skyrockets because now we're reducing the volume. We're actually squeezing that ventricle. Why are we squeezing it? Well, we're squeezing it to decrease the volume, increase the pressure. Everything goes from high to low. So that blood is now going to go from an area of high pressure in the left ventricle to an area of a lower pressure into the aorta. Then our aortic valve closes. When that aortic valve closes, we get a little blip of increased pressure from the backflow of blood into the aorta. It's kind of that idea of that erupting volcano, some of that lava going right back into it. That's this dicrotic notch right here. That's what's happening there as that aortic valve closes. The pressure in the left ventricle drops, RAV valve opens, the ventricles passively fill, and the whole thing happens again, right? Put that on repeat if you can't do it yet. I mean, I don't expect you to be able to do it yet. You're just learning it, but that's how you learn it. You just got to say it and do it and practice it. So let's talk about the heart sounds, right? So this whole idea of cardiac cycle is getting the blood through the heart and out to where it needs to go in the body and then back to the heart. That's what the cardiac cycle is. And so we can detect the cardiac cycle and the function of our heart by, measuring it. And a stethoscope is one of the ways we do that. We listen to the heart sounds. And we'll have a chance to do this in lab. There are two major heart sounds that you'll be able to hear with the stethoscope. One is sound 1, and the second one's called sound 2, or S2. The lub and the dub. The lub and the dub. What those actually represent are the closing of the heart valves. When those heart valves slam shut, you're hearing that as a heartbeat. So the lub, or that first sound, is when our AV valves close. That makes sense. Look back here at this chart. The first thing that happens is our AV valves close. Then our semilunar valves close. So sound 1 is our AV valves closing. Sound 2 is our semilunar valves closing. I think of it like this. If you can picture the heart, right? I always try to visualize things. So our AV valves are kind of straight up and down, right? Atria, ventricles, AV valves are in the middle. But if you remember your heart models, the semilunar valves, the aortic and pulmonary semilunar valves, are kind of crisscrossed in the middle. So lub, dub, lub, dub. AV valves, semilunar valves. AV valves, semilunar valves. Lub, dub, lub, dub. That's how it is. So there is a kind of fourth and third sound that you will hear. It's very faint. This is that kind of blood flowing and that filling sound. So it's the blood flowing into the ventricles and then the atria actually contracting and pushing that blood in to the ventricles. It's very hard to hear. You have to have pretty good equipment to hear that. It's because the sound isn't very loud, and adults tend to have more fat and our bones are thicker and so forth. The sound doesn't really get through. There we go. So there's the sounds. Lub, dub, lub, dub, lub, dub. AV valves, semilunar valves. You know what, I think I'm going to stop the video here actually, and we'll start back up the next video with the next section of this chapter. This stuff is intense, so please go back, re-listen, revisit, say it out loud. The more active you can be when you're studying, the more this stuff's going to stick in your head.